Let's talk about estimating limits from a graph. So you can see the graph that we're going to work with in this video is off to the side here. It has a lot of really weird stuff going on, but we don't have access to the formula that's creating this graph. So everything that we're going to answer over here is just an estimate based on what we're looking at. Okay, so we're going to start top left here. So the limit of this graph as x approaches -3 from the left side. So this little tiny minus sign after the -3, this means from the left side. So I'm going to go to x equals -3, which is right here. And I'm just going to worry about the x values just to its left side. So that puts me like right here on the graph. So we're imagining like if you plugged in these x values that were like be close to -3 and we tracked their y values, what would their y values be suggesting is the y at -3? And we can kind of tell from the graph here that they would be getting really, really close to +1 because that's the height of this point right here. So I'm going to say that this limit equals 1. And I'll get a different answer for this next limit. So this is the limit of the same function. X is still approaching -3, but this is from the right side because of this tiny little plus sign. So I'm still looking at x equals -3, but I'm just on its right side. So I'm approaching this point up here on the graph. So if I was plugging in like -2.999, what would I be guessing the y value at -3 is? And these y values are all headed towards this height of 3. So that's what this limit will be, is 3. Even though that open point is there, or technically it's not there, the limit doesn't actually care if the point's there or not. It cares like where it was supposed to be based on the stuff around it. All right, so underneath these two, you can see we have the limit. Oh, this is supposed to be -3. The limit as x approaches -3, but without a symbol after it. So this is just like a regular limit. When you don't have a little plus or minus sign after the number, it's just like considering both sides at once. So at -3, we said from one side, you would have guessed the height is 1. From the other side, you would have guessed the height is 3. So that means that this limit does not exist because the one-sided limits don't agree with each other. And all of this could be completely different from what f of -3 actually is. So in this picture, we find the actual solid dot at x equals -3, and it's at height 1. So this equals 1, even though not all the stuff above it was that number. All right, let's try it again, but we'll look at x approaching 1. So now I'm looking right here in the picture to where we have kind of this weird piecewise jump in the graph above x equals 1. Right, so we start off with x approaching 1 from the left side. The little minus sign is always the left. So we are approaching x equals 1 over here. So we're imagining if you plug in x equals 0.999 and track the y values, what is it suggesting should be this height? And clearly it's just the height of that open point, which is 1. If we approach 1 from the right side, though, that puts us way up here at height 4. So all of these would be telling you that that height should be 4. And again, because these two don't agree, this overall limit at just regular 1 does not exist. And this one's extra weird because f of 1 doesn't match any of these things like it did over here. So f of 1 is 2 because that's where that closed dot actually is. So this one's a really great example of like when the function is normal, all these are equal to each other, but it could be so weird that none of these 4 items are equal. Before we move on to some of these weirder cases below the line, I do want to take a minute to point out at least one place where it's not that crazy. So what if you consider in this graph, the limit as x approaches 0 from the left, from the right, and then from both sides. So at x equals 0, the curve just passes through the point 0, 1 right here. There's no jumps, there's no holes, there's nothing weird going on. The y value is 1, and it looks like it should have been 1 the whole time. So this limit is 1, and so is this, which makes the two-sided just regular limit also 1. And in fact, because this point really is here and it doesn't even skip the point that was supposed to be there, f of 0 is also 1. So this is what it'll look like when there's like essentially no funny business in the graph. It just smoothly goes through the point that it looked like it was going to go through. These are when you have jumps and holes and crazy stuff. All right, so let's do some of the prepared stuff below the line here. So these first few limits are looking at x equals 3, which is where we appear to have a vertical asymptote in this graph. So this first one is x approaching 3 from the left. So this is like the 2.9 side. And as we plug in those x values really, really close to 3, the y values are just plummeting south. They're just going really, really fast down. So this limit doesn't exist, but because it's headed down like that, we can be more specific and say negative infinity, which is telling us there's a vertical asymptote, and on the left side, it's headed downward. On the right side, which is this next limit, we're coming up to the asymptote, right? So if you were plugging in x equals 3.1, 3.001, you'd be getting very, very large positive numbers here. So here again, we want to say the limit doesn't exist, but because there's an asymptote headed upwards, so we'll say positive infinity. Right? And then the overall limit, just as x approaches 3 regular, this does not exist because these two don't agree. If these were both infinity, I would say infinity. If they were both negative infinity, I would say that. But because they're mismatched, this is a true does not exist. As is f of 3, you could say this does not exist, or alternatively, you could say it's undefined. Because if we have a vertical asymptote in the graph here, this is a function where you could not plug in 3 to the formula. There isn't actually a point on the dotted line anywhere. All right, the last point I want to make in this video is just kind of adapting some of our notation that we were using when we were still talking about rational functions. So for this weird picture, as x approaches infinity, f of x approaches what? So x approaching infinity means the far right end of the graph, which brings us over here. And it appears to begin a horizontal asymptote over here, right on the x-axis. So that would be a horizontal asymptote of y equals 0. So I'm going to put a 0 in that spot. So this notation we can adapt to our new fancy limit notation, and we can say it as the following. The limit of f of x as x approaches that same infinity is going to carry down. We would say that limit equals 0. This is using our new notation to say this older topic. And we can do it one more time for the other end of the graph. So as x approaches negative infinity, that puts us way over here. So at this end of the graph, it looks like we're just kind of headed downwards forever. So there's no horizontal asymptote, but we do know how to say downwards forever, right? I can throw in this negative infinity. And again, we can adapt this to the new notation. The limit of f of x as x approaches this negative infinity will equal what I decided, which is negative infinity.